at University Catholique de Louvain, and she will talk about Skein categories. The stage is all yours.
Oh, thank you very much for inviting me to talk. And yes, I'll be talking about Skein categories. I think this slide might be more useful. So basically, I assume most of you know what a Skein algebra is. I'll give an example on the next slide for those who don't. But basically, a Skein algebra is an invariant of frame links. So you take a surface, say, for example, an annulus, and you consider links on that surface, and then you impose a load of relations called the Skein relations, which there are lots of different Skein relations you can choose, the Humphrey ones, Kaufman ones, whatever ones you please. But the idea is you have this picture, and in general, if you want something more complicated, you may end up with nodes with multiple framed links going into them, which I'm depicting here as a coupon. And usually these things should give you invariants of frame links, which means that they're not quite not invariants because they're not usually invariant under the first Reidemeister rule, which is the one that says that if you have a kind of twist, you can untwist it. But these are kind of a classical thing that they did a lot in the 80s and the 90s and things like that. In this talk, I'm going to be talking about Skein categories, which are this picture in the middle. And basically, the main difference you need to think of it is a Skein category takes a Skein algebra as its morphisms. And the difference between the Skein algebra and the Skein categories is basically that you allow your links to have endpoints. So you allow them to join your surface. So your surface, say the annulus, you thicken it, and you allow it to join the surface at the top or the bottom. You also, in order to allow you to include all of the Skein algebras, we usually have a coloring, which I'll describe later. And so basically the purpose of this talk is basically to talk about Skein categories. And I will be describing some of my work, which relates to something called factorization homology. So Skein categories are basically a topological thing. They're just defined with pictures like this, basically. Whereas a factorization homology is designed to give you an invariant of a manifold by a categorical construction. So what you do is you assign something to a disk, and then you categorically extend by taking a left-can extension to get you an invariant of a manifold, which is very nice and functorial, but maybe not very many pictures involved. So now what we're talking about is how you link Skein categories to factorization homology. And at the end of the talk, I'm going to talk about the case that instead of considering when you have links anywhere, so to the top and the bottom, etc., we are going to consider what happens if you only have links on a little disk on your surface. And this actually allows you to construct an algebra structure again. And these are called internal Skein algebras. And I'm at the end of this talk, I'm going to talk a little bit about how they're related to other things like Alekseev moduli algebras and internal Skein algebras, depending on how much time I have. So that's basically the purpose of this talk, is to play around with some pictures. Okay, so because I should introduce this, there we go. I should give you an example, in case you don't know that much about Skein algebras. And this is essentially the example I'm thinking of throughout. So this is the kind of one of the most basic Skein algebras you can think of. So what you do is it's called the Kaufman bracket Skein algebra because it was invented by Kaufman in the 80s. So what you do is you take formal linear combinations of links in your thickened surface. And then you impose some relations. So in this case, every time you have a crossing, so you cross over, you can resolve this crossing into two things which don't have crossings. So you can basically remove any crossings in your Skein and your link. Okay, the crossings are what would happen if you take the link and then you project down. So if you project down, you'd end up with overcrossings and undercrossings, and that's what this diagram is relating to. It's the projected version, but we should actually probably better to think about the non-projected version, so the actual thickened, as though your links are actually living in the thickened surface for this talk, because it's actually easier to think about. Okay, so the point is, if you have a crossing, you can get rid of it. And if you have a trivial link, they're just in a trivial bit of space, so it's not wrapped around like any punctures or anything topologically interesting, you can get rid of it if you replace it just with some Q factor. So you multiply your algebra by taking your surface and stacking them on top of each other. So you take one copy of your thickened surface and you just stick it on top of the other. So that is what the classical Kaufmann-Skein algebra is, and it's an invariant of frame length. So as I said before, it's not actually invariant under twists, so you do actually need to frame your length. So this is why in the picture here, I've painted everything as a ribbon rather than as a single strand. But you can renormalize the Kaufmann-Skein algebra, and then you just get the classical Jones polynomial. It is very much related to the kind of classical knot theory stuff. But now what we're going to be talking about is how do you define generalization? So how do we construct a category from this? And the first thing we need to do to construct a category is to define what we mean by these colored links. So the thing we need to do is we have a ribbon graph. A ribbon graph consists of strands. So for example, this strand, which is labeled X, and it has a framing, which I've depicted using a ribbon with the blackboard framing, and it has a direction. So in this case, this one is directed up. So from the red to the black. And you also have coupons. So coupons are just these, and you can attach the ends of ribbons to coupons, or you can attach the ends of coupon ribbons to themselves. So for example, in this annulus, which is labeled T, and you basically construct a ribbon graph here. And then what you do is you color it. What do you color it with? You color it with a ribbon category, okay, a strict ribbon category. So a ribbon category is a category, and it has a monoidal product on it. So you have a way of taking the tensor product of two elements or two morphisms in your category. You also have a braiding. So this is essentially the way, so if you have a tensor product of say V tensor W, a way of swapping the factors. So you sometimes when you swap the factors, you need to like do something like multiply by a scalar or do something interesting, but in general you want something that's a braiding. So some way of changing the order of the factors. This should probably be a tensor product. And then you have a twist. So this is an element in the ribbon, which is just from the thing to itself, which twists. And you also are going to have duality, so it's rigid. So that means for every element you have its dual, and you have a unit and a co-unit, and a ribbon category is a thing with all of these things. So such they're all compatible with each other in a well-defined sense. So if you have one of these, the example to probably think of is if you think of finite representations of say quantum groups. Then this gives you a nice ribbon category, and this is basically the example we'll be thinking of, in particular finite representations of the quantum group of SL2. Or if you can't think of that, think of just finite representations of non-quantum groups. Okay, so the point is, if we have such a ribbon category, we can color our ribbon graph, and what we do is we take each strand and we label them with an element of the ribbon category. So here I've labeled this strand with X, and this one is labeled with Z, this one's W, and if you have a coupon, you label it with a morphism, and the morphism has to be the morphism that makes sense. So this coupon goes from X, the strand labeled X, to the strand labeled Y. So it has to be a morphism from X to Y. And this one's a more complicated example. Okay, so in this example, you can see that sometimes the arrow goes into the coupon correctly, so it goes upwards into the coupon, but on this side, it's actually going to be going downwards. And we do this by taking the joule. So this would be Z joule, so for this bit, Z for this bit, and it goes out to the joule of Y and the joule of W. And so this is a choice of a morphism which has the right domain and codomain. And so if you choose one of these things, these are called a colored ribbon graph. And what we do for a Skein category is we embed them into our thickened surface. So very much like in the Skein algebra, we took the links and we embedded them into the thickened surface. In this case, we're just going to embed our ribbon graphs. The difference is that the unattached bases, so some of the bases of your ribbons are going to be attached to coupons. So they're all dealt with. But the other ones, say, for example, this black one up here, is just kind of unattached. And the rule is if you embed it into the thickened surface, it has to either embed to the top, so the surface crossed 1, or it has to embed into the bottom of the diagram. And so that's basically it. And what we now do is we can construct a category. The objects of the category aren't particularly interesting. They are just going to be these points. So if you see these strands meet the top or the bottom in a kind of framed point. And so the objects are going to be finite collections of disjoint points. And these points have a framing. They have a direction, so they can either go up like this one, or they can go down like this one. And they have they're colored with an element of your ribbon category V. And that's pretty much it. So these are the objects. They're not the interesting thing about this category. All the interesting information is in the morphisms. So the morphisms are these colored ribbon graphs in diagrams. So we've taken our ribbon graph, we've embedded it into our surface, and we're going to take k-linear combinations. So k is just some field, or I think in general you can take a commutative ring with identity. And so you're just going to take formal linear combinations of these ribbon diagrams, and they're obviously, if it's going to be a morphism from this set of points to this set of points. So in this case, it's going to be a morphism from this point labeled X to this point labeled I can't remember, W, I think. And you're going to do it up to isotopy. But the isotopy obviously needs to preserve what our ribbon graph structure. So what it means is the isotopy can't detach the strands from the coupons or change the colors or change the directions. But otherwise you are considering these diagrams up to isotopy. Are there any questions so far? No questions? No questions? Oh, I know.
Okay, can I ask a dumb question? Sorry. Really dumb question. You probably said it, but I missed it. The green tube that you have, a ribbon, it's pointed down, or it looks like, but all the other ones are pointed from red to black, but that one's pointed from black to red.
Yeah, basically you can choose a direction. So that's kind of negatively directed.
Okay, thanks.
Yeah, so that's why I have these kind of different strands. I was just saying is that in general, you have quite a general thing. You can choose a direction and you can choose a labeling. Yeah.
Cool, thanks.
So that's allowable. Okay, so the point is we've got ourselves a category of colored ribbon graphs, but in our Skein algebra, we impose some relations. We impose the Skein relations. So now we need to learn how to impose the equivalent of the Skein relations for these colored ribbon graphs. So what we need to do here is the Skein relations we're going to impose are completely controlled by the coloring, the category we use to color our category, our diagrams with. So if you look at Tarayev in his book or his paper. He proves that there's a full surjective ribbon functor. So what I mean, from this ribbon category, or just not in the case where you have a general surface, but just when you have a cube, basically, or a thickened square. And so if you have this, then you can define a functor called evaluation, which goes from the ribbons on this cube to the thing that we've colored our ribbons with. And so what it does is it takes the objects. So the objects, if you remember, are just going to be colored like little intervals, so framed points with a direction. And if they are positively directed, so they point upwards, we're just going to send it to the coloring. So if it's colored by V, we're going to send it to V. And if it's going up downwards, we're going to send it to the dual of V. Okay, so that's on objects. And it's surjective on objects, pretty much obviously. And for if you have a ribbon, if you've got a ribbon that does absolutely nothing interesting, it just goes from V to V, and it's labeled with V, you just send it to the identity. If you want to compose morphisms, you're just going to stack vertically. And if you want, this is a ribbon functor, so it has all of these structures, and it preserves the structures. So it preserves the monoidal product. So it turns, if you have two ribbons next to each other, it just turns it to the tensor product on the other side. So this one's labeled with V, and this is labeled to W. These objects would be sent just V tensor W. And this is the braiding of the ribbon category. So if you put a cube, so if you consider the ribbon category of a cube, it's actually a ribbon category. If you consider it a general surface, it's not going to be. And the reason being is, in general, the monoidal product isn't going to be defined. So you have to
in the chat. So
what?
Torben wants to know what you mean by surjective.
I mean, it's every morphism in V comes, you can map to it. Does that answer the question?
Yes.
Yeah. So just, yeah.
May I also ask a question?
Oh yeah, sorry. I meant surjective on objects and full is on the morphisms. The surjective just meant that all of the objects in V map from something in the ribbon category. But what's your question?
Oh, I was about to ask another question.
Yes, no, go ahead.
So you say if two objects are put together, then you send it to the tensor. However, if two objects, so actually we are choosing a projection, right? If that two objects under the projection will collapse, then what would you send that to?
So the point is that in the projection, so what you do is you choose on the, so this 0 to 1 cube is just a square and then thickened. So the point is you basically choose a curve, an ordering on your on the square, because these points are actually just thickened points, and they have to be disjoint.
I see. Okay.
So you just need to choose a curve for covering your square, which you usually just take lexicographic ordering or something. But even though I depict them as intervals, they're really framed points.
Mm-hmm.
So you don't actually get that much collision because your objects in ribbon are meant to be distinct.
Thank you.
Any other questions? Okay, so the point is, so we have on ribbon, we have a braiding, and the braiding is depicted using just crossing the strands. So this one goes from VW to WV, and this gets sent to the braiding in our ribbon category. And this element here gets sent to the twist. So this is why it's called a twist, because if you think about it, you're just twisting the ribbon. I think it's also called balancing. And as I said, we know what to do with joules. And we have a unit, the unit and co-unit. And these are just the cup and the cap in the ribbon functor, and they match up nicely. So you have this kind of canonical way of mapping from your colored ribbons to the category you colored it from. And this is a kind of old functor. But we're going to use this functor to assign your our relations. So the point is, no, we've gone backwards. There we go. We are, so your Skein category is just going to be this category of ribbons, modulo a certain relation on the morphisms. So the objects are the same. It's only the morphisms that are interesting. So if you take a linear combination of ribbon diagrams up to isotropy, they're equivalent to 0 if you can find a way of embedding a cube into your thickened surface. So take this cube, we embed it into our thickened surface, such that if we use this embedding to evaluate this sum just on the cube part, that's going to evaluate to 0. So the evaluation using this Turaev functor is 0. Outside of the cube, everything, all of these ribbon diagrams are identical. And there's a kind of technical condition which says that the ribbon diagrams only intersect the cube in a nice way. So transversely in strands, you can't end up with like this cube intersecting in the middle of a coupon or anything nasty. So this is the relation we're going to impose, and this is essentially just the relation. If you think of the Skein categories, our Skein categories back in over here, we impose them on these little disks. So disk, cube, they're pretty much the same thing. And so this is just kind of same concept. And instead of writing out our Skein relations, the Skein relations are determined by this evaluation functor. And that is the Skein category. And the Skein categories were, I mean, they're based on essentially Walker's stuff, but you find that they're first written down like precisely in the work of Johnson-Freyd. So that's the Skein category. So the other thing to note is that if you want to consider what the Skein algebra is, all we need to do is consider the ribbons, so the endomorphisms, from nothing to nothing. And that's going to give you a Skein algebra. It's going to give you the Skein algebra associated to the ribbon category V. So your Skein algebra is living inside this category as the endomorphisms of nothing to nothing. Okay, so that is, any questions? Or I will, should we have a break now or?
If you like, yeah.
Yeah, it's 25 past.
It's 25 past, yeah. Okay, let's have a 5-minute break. We continue 5 minutes. So how many cases are known beyond Turaev's result? So other surfaces?
What do you mean? I don't think anyone's defined the function for general surfaces.
Oh, really? Okay.
I mean, I'm not sure it's so much, I mean, I don't know of any results involving the other surfaces. I mean, the problem is if you get most surfaces, you don't have a monoidal structure.
Right.
So the fact that it's a ribbon functor, which I guess is the content of the theorem, doesn't really work unless you can come up with a way of defining a
right, but maybe you want to formulate something in terms of n algebras or whatever.
Yeah, I mean, certainly you could define it for, say, an annulus quite easily, because you could just do a monoidal structure by embedding the annulus inside another annulus, but right. I don't know if anyone has.
Oh, really? Okay.
It can be, some work can be found by Alexander Kirillov and In-Hong Tam this year and last year.
Okay, could you maybe write those names down in the chat?
Or can you post the link in the chat?
Oh, yeah.
Yeah. Just so I can find them. Because I'd be interesting, because I haven't heard anyone using these.
And I'm also working on a more general type of surface. Okay. We hope to get it to all the surface. Oh, wait, but we are only working in Crane-Yetter theory, so the underlying category should be premodular. It should be slightly stronger.
Okay, yeah.
An assumption here.
Yeah, I mean, because this is just the reason for our assumption is we just want to put representations of fundamental groups in. because they seem to be the ones that get you the classical Skein algebras.
Mm-hmm.
But obviously that's just the assumption we were using because the stuff we have is a ribbon category.
Right. Ribbon category is almost like a premodular category. We only need some.
I mean, it's a rigid, balanced, braided monoidal category.
Yeah, so we only need finite and semi-simple. That would make it premodular.
So yeah, certainly it would be a case of this. I mean, this is slightly more general, but I think premodular I don't think premodular does involve representations of quantum groups, right? If you're doing generic. Q. On quantum groups.
Let me recall. Yes, if you take the semi-simplification of representation of some quantum groups.
So if you take Q to be generic, which I guess I am, well, I've never. I mean, this theory doesn't assume it, but you, in practice, I've never considered the non-generic cases personally. So, but yeah. So I think it would cover a lot of the cases we care about, like the Skein algebras, but often with the Kaufman, they actually like to consider roots of unity.
Roots of. Yeah, I don't consider roots of unity. So
no, I mean, I have none of myself. I just know that often choosing the fourth root of unity seems to be quite popular in the literature.
There's also a question, actually two questions in the chat. So Liam wants to know whether the crossing in your kink, in your ribbon element, actually is a braiding.
So this crossing?
No, the other one on the other side. The ribbon.
This one?
Yes.
So the little twist?
Yes.
Okay. Yeah, no, it gets sense to the twist on your in your V. So if it's a ribbon category, it has a balancing or a twist. So this is a map from V to V, and this is a morphism from V to V.
So the whole picture is just a twist. Okay.
Yeah, so it's just a twist.
Right.
You can either depict them as literally twisting a ribbon, or you can kind of do this, and this should be the same, unless I've drawn it.
Okay, and Rachel wants to know whether there's any relation between these categories and embedded spaces of links and thickened surfaces.
Embedded, can you repeat
that? Whether there's any relation between these categories and embedding spaces of links in thickened surfaces.
I mean, in practice, these are, if you consider the embedded links in the thickened surfaces, you're basically in this kind of Skein algebra category. It's not part of the, this isn't, it would just be the endomorphisms of no points to no points. So we kind of live inside, if I understand the question right.
I think the answer is a little more subtle. I think the embedding space, I think if you think about the embedding space, then the connected components of it are going to turn out to be either, they are going to turn out to correspond to parts of, there's going to be a way to sort them in so they represent maps and actually the category of framed tangles, or an algebra of framed tangles, depending on how you restrict the boundaries. And then these categories that you're looking at here are quotients of that by the Skein relation. Quotients of its linearization by the Skein relation. So that the actual embedding space is rather far from what these are, although you can see it as part of the underlying structure.
I mean, would the embedding space be very similar to the ribbon category? So before you quotient.
Well, but only after you take an equivalence on it that's more or less passing to connected components. Pi zero of the embedded space is going to be more or less the original sort of ribbon category thing.
Okay. But, technically, I haven't really considered the non-connected cases, but I haven't ever assumed my surface connected. I mean, you can define the ribbon category for a connected thing, but I think you're slightly different.
Are we going to talk about some, are we going to talk about your work on genus too? Recently?
Not in this talk. I was working in genus. I was doing kind of concrete stuff with, which one? Is this the one with Peter?
Yes.
Yes.
On the genus 2.
No, in this talk, I'm not talking about that at all.
Okay.
That's a essentially completely tangential relation. It only kind of connects in that you start off with Skein category, Kaufman bracket Skein algebras. So that's basically the only relation that I know.
Right. Like if you give it's a nice paper, so if you'll give a talk on that, I'll be very glad.
Yes. I mean, I haven't so far ever, well, I gave a few talks when I was a PhD student to other PhD students.
Okay, sorry to interrupt, but I want to continue.
Yes, sorry.
Of course. Yes, so we should continue. So, and now I've disguised what a Skein category is. In the introduction said I would relate them to, my work was relating them from Skein categories to factorization homology. So this definition is actually quite topological. I mean, there are functors living around the place, but I want to relate them to a categorical construction, which allows you to construct kind of abstractly, well, you know the thing is going to be an invariant. You don't necessarily know much about it. So this is, so starting off, what we need to do is we're going to consider if you have a symmetric monoidal functor. Okay, so I'm sure I defined, yeah. So what we're going to do is we're going to consider, okay, I put infinities in the sign, but in practice you can put infinity equals 2. Because in practice, all of the categories we're going to be considering are going to be 2 categories with all of the higher morphisms just going to be the necessary identity morphisms. So the point is, if we're going to consider ourselves smooth-oriented manifolds, because in Skein categories you usually consider oriented manifolds, and we construct a category of all these manifolds, which has the manifolds as objects, and all the morphisms are the embeddings between your manifolds. So this gets you an infinity group pod with the first stage. So the 1 morphisms are just going to be embeddings. And the 2 morphisms are going to be isotopies between your embeddings and so on. So in this category, there's obviously going to be the subcategory, which is just going to be disks. So if your manifolds are disks or just finite unions of disks, what you construct is a symmetric monoidal infinity 1 category, where the monoidal structure is literally just disjoint unions. So it's kind of a dull one. So what you can do, if you have a way of constructing from this category of disks, a symmetric monoidal functor which associates to this disk some object in a suitable higher category. So Tensor category. This is, you kind of think of it as the kind of Turayev functor kind of analog, but I shouldn't go too far down that route, otherwise I'll go wrong. But the point is that on objects, what we want to do is basically associate to each disk a object in your higher category, and this is rather tellingly I've called V. And this needs to be a functor, so it needs to respect how you can embed disks into other disks. So if you have one of these things, the point about factorization homology is you take one of these and we think about how to use this to get you an invariant of a manifold. So what we do is the disks live inside the manifolds. The factorization homology is just take this framed n algebra, and then you extend it categorically as a left can extension to a functor from manifolds. And this functor is called the factorization homology. That really is not the right V, but anyway. And the point about this is that what I mean by a left can extension, so this is essentially the best manifold for the best functor for the job. So it essentially satisfies the universal property, which means that this is the correct extension of this functor to manifolds. So the point, though, about this definition, I don't think I've necessarily explained it very well, but you don't really think of a factorization homology as a left-hand extension, or at least I don't. I usually think of it as homology theory. So the most important thing about a homology theory is if you break down a surface, you can break down what the homology is, which makes it, unlike, say, homotopies, it's possible to calculate things on them. So this is a homology theory, which is why it's called factorization homology, in that it satisfies an excision property. And therefore, we can break down this surface to basically what its value is on a disk, which we know, and we glue together these disks, and that gives you the factorization homology of the whole surface. So, well, exactly, if we consider this left thing as surface, okay, from now on, I'm just going to assume we're doing n is 2. So we're just doing with surfaces because it's easier to draw pictures. So you assume we have a left surface called M, and we have a right surface called N, and we've glued it together along this little subsurface, this surface A, which is just, in this case, a circle crossed with a unit interval. So if you have such a collar gluing of two surfaces, you can obviously topologically glue them together. And the factorization homology of this topological gluing is equivalent to the relative tensor product of M, of the factorization homology of M, the factorization of N, relative to the factorization homology of this little middle band here. And I need to define what I mean by the relative tensor product in this case, because I think most of you probably wouldn't, you need to define this. Okay, so what I mean by the relative tensor product is the, I guess, categorical definition of a relative tensor product. So more exactly, if you take A to be a curve, a thickened curve, so for example, in this case, we're just taking a thickened circle, then the factorization homology is a monoidal category, and the monoidal product just means if you have two of these, two surfaces, you can include them into a copy of itself, basically just by contracting along the trivial 0-1 direction. And this map of this embedding induces a map on the factorization homologies, and that is our monoidal product. And so this gives this factorization homology a monoidal structure. And also, if we assume we have an action, so if we can include this surface A into the surface M, and we can include it into the surface N, and then that's going to induce an action on the level of the factorization homologies. So what you have is a monoidal category, and you have that this factorization homology of M is a right A module category, and this one is a left A module category. And so, and this, in the case where we have this excision theorem, we definitely have these constructions, we're going to define the relative tensor product to be the co-limit in our kind of meta, our kind of universe category C tensor product. It's just going to be the two-sided bar construction. By the way, you should probably think of this universe category just going to be like a category of categories, basically, as this is the cases we're considering. So the point is the two-sided bar construction. So we have an action of A, a left action, and that reduces out to here. We also have a right action, which gets you to here. If we have this, we have a left action, we have the monoidal product, and we have the right action. So these are these different arrows. And so what we're going to do is we're going to take the co-limit, which makes everything going to work there. There. Okay, so this is the definition. So it's basically going to be like a co-equalizer, but you just extend infinitely to the right because you want the compatibility relations. In the case of two categories, you can basically truncate at this stage, so you only need to, you don't need to worry about these 4 arrows on the left because they're not that important. And this is essentially a kind of categorical generalization of just the relative tensor products of abelian groups, if you think about it in terms of colimits and stuff. Okay, so we have this abstract definition of a relative tensor product, and we have this excision theorem. And the point is that if we know essentially what this functor is on a kind of disk or a contractible surface, and you know it satisfies this excision property, and you know that if you have it's something with corners thickened, you get a kind of nice canonical monomial structure as you do with this particular these diagrams. This actually completely characterizes your factorization homology. And this is what we're going to use to prove that if you have a Skein category, these are actually a particular example of a factorization homology. So the first thing we need to do to relate it is our factorization homology is a functor. So it's a functor from manifolds to this our kind of our universe category C tensor product. And in our case, we're just going to take the universe category to be small k-linear categories. Okay, so a k-linear category, in case anyone's confused, is just a category whose morphisms form k-vector spaces, or they're enriched over vect. Okay, so the objects are just small k-linear categories. The morphisms are functors, and they have to be k-linear functors because we're considering k-linear categories. And the two morphisms are just going to be natural transformations. So this is basically a category of categories. And we defined our Skein category of our surface. It's going to be a k-linear category because where our morphisms are just formal k-linear combinations. So we pretty much defined it to be a k-linear category. Also, if you think about it, if you take an embedding of surfaces, the embedding of surfaces is going to induce a functor from the Skein category of the first one sigma to the second surface. And basically, this is what these two functor sends to its objects are just going to be the Skein category of the surface. So we're in manifold dimension 2. And the embeddings are going to be sent to the induced functor between the Skein categories, and then you can have higher morphisms between your embeddings, and that will get you the natural transformations. And so this is a two-functor. And the important thing, and I proved during, I guess, my thesis, that if you take this Skein category is the factorization homology of the factorization homology of the framed E2 algebra, which, okay, so if you have a ribbon category, you can construct a framed E2 algebra from that ribbon category, which I call FV, and the Skein category is the factorization homology of this framed E2 algebra. And using the characterization of that I mentioned earlier, basically the only hard bit to prove about this is actually the excision result. And this basically, if you do it, the first thing you need to do is take this abstract colimit definition, and you need to prove that this colimit definition of the relative tensor product, in the case where you have the category of k-linear categories, is just going to be the standard relative tensor product of k-linear categories whose objects are pairs of objects in the first category and the second category. And so essentially the nice abstract, concrete definition. And then the second stage is a kind of and that's basically a playing around with colimits proof. And the second bit is basically just a topological proof to show that your Skein categories satisfy this kind of definition of relative tensor product when we have a nice concrete definition for the relative tensor product. And that is basically the relation. So the relation is that a Skein category is just a factorization homology, or in a particular case, so when you have small k-linear categories and the E2 algebra is determined by the thing you use to color your ribbons by. Are there any questions?
there is actually a question in the chat. So Yinchen wants to know what would be the 3D analog of your theorem.
Well, you basically end up considering module categories over the Skein category. So you consider sort of a module Skein. So in Skein algebras, the 3-dimensional picture is just the Skein module. You can do a kind of 3-dimensional extension, and in fact, there's a paper on finiteness of Skein modules, which kind of gets into what would be the 3-dimensional analog. And what they do is that you have a 3-manifold whose boundary is a 2-manifold surface, and this thing you basically consider modules over the Skein algebra. But you should probably look at that paper if you want to see kind of more detail, which is at the references at the end of this talk.
Thanks.
For the 3-dimensional extension. So, okay, I'm now, as I've basically got 12 minutes, I am going to just talk a little bit about what happens if, instead of considering the general Skein category, we just consider this specialized case where instead of having tangles which are allowed to have any number of points anywhere on the top and the bottom, are just going to have points in a certain disk. And this is essentially following the paper that I was just talking about, like Gunning, Jordan, and Safanov. And the point about it is that this relates to various other areas which might be of interest to people. And in particular, you get things like generators and relations for such a thing, which I don't think we have for general Skein algebras, though they shouldn't be too difficult to calculate because of the excision properties if you want to. So the idea is we are going to construct an algebra, and that from our Skein category. And so what we're going to do is we are going to consider a punctured surface. So we're going to choose a particular puncture. So this loop is our particular puncture we've chosen on our surface. And what we're going to do is we're going to embed. So obviously, if you kind of embed an annulus, you can kind of, it's homeomorphic to the thing originally. So you can essentially do this, and you're going to just attach a disk into this surface using this action. So this is going to define you an action from the disk. So you basically, to the factorization homology of your disk, to the factorization homology of your whole surface. I should stick to Skein categories, I feel. So the point is, if you have an element of your ribbon category, this is a point on this disk. And you use, so we define this functor here by taking the V, we consider it as a point in this disk, and we embed it into our surface. And then we consider the vector space, which is just the homs from this point, this V marked point here, to nothing. So in this particular case, this V is the tensor product of X and label the green one, but it's say W dual. And so this would be an example of something in the Skein algebra at X, at the when you apply X tensor W dual. And so this is just a kind of, and the point, interesting thing is this, is that this is actually an algebra, and it's an algebra. Okay, so the first thing you would realize is this is a functor from the opposite category of V to vector space. So it's basically an object in the free co-completion of V. So it's an object, it's a pre-sheaf from here to here. And basically this LFP isn't particularly important, but it's no longer necessarily a small category. So these are just locally finitely presentable categories. So we've just expanded our universe slightly. It doesn't really matter a great amount. But this internal Skein algebra is actually an algebra in this extended category of no longer small categories, but not too ridiculously big either categories. And it's and if you think about what the product would be, you stack, because you could essentially take points here and kind of draw them up, and you end up disk, and you end up with a monoidal product. Sorry, I think that was not particularly well explained by me, but the idea is if you just take the morphism space from some points which are just on a little disk close to your puncture to nothing, you construct yourself an algebra. And the point about this algebra is this algebra, if you put in the right values for V, is going to get you just a stated Skein algebra. So these are not Skein algebras because I guess they are no longer closed links. The point is that if you take links, just standard, like non-directed links in your surface, and you allow them to meet with the boundary of your thickened surface, so the kind of thickened boundary, and if you give each of these points where it meets the thickened boundary a value plus or minus, you get yourself something called a stated boundary tangle. And if you impose these relations on these, and obviously the isotopy, standard isotopy which you get something called a stated Skein algebra, which is defined by Lee not that long ago, a few years ago. And the point is that this is a well-defined algebra with nice concrete things, which maybe the other definition didn't have. And the point is that this is going to be what happens if you take your internal Skein algebra and you, as your ribbon category, choose just the Temperly-Lieb category. So the Temperly-Lieb category just consists of a certain number of points as its more objects. So in this case, we've got n is 5. So this is the n is 5 object, and this is also an n is 5 object. And the morphisms are Temperly-Lieb diagrams. So these are essentially curves from which join points to points, and so that you don't really have, you can loop back on yourself, but you can't have any crossings. And you, and if you have a, you want to compose your morphisms, you just stack them on top of each other, and you remove any circles that you produce, and you remove the circles by just replacing with a factor of q here. And this is actually, you can construct into a ribbon category. So you use the monoidal product, it's the horizontal stacking, which I keep using throughout this talk. And the braiding, if you might have noticed, I'm basically defining this to be the Skein relation right at the beginning, the Kaufman bracket Skein relation. So if you want to define this braiding, you define it as to what it's equivalent to in the Skein algebra. The duality are just going to be standard cups and caps, and you just you also can define a twist. So the point is that if you define, this is a nice ribbon category, so we can consider the internal Skein algebra, or you could consider the Skein category, but we're going to consider the internal Skein algebra, and you color it by this. What you do is you basically get a stated Skein algebra. Well, technically, what you need to do is you need to go from the Temperly-Lieb category to the finite dimensional representations of SL2. And then you need to go from that using your phonectron functor just to vector spaces. And then you need to extend it. But this is essentially just messing around with a little bit of categories to make them actually match up perfectly. So this Temperly-Lieb category is basically just the representation finite group aren't quite the Temperly-Lieb because you have to take a slight Cauchy completion or idempotent completion of the Temperly-Lieb to get to this. So that's why I was saying initially you should really think of the Kaufman Skein algebra as the SL2 group SL2 theory, but technically you actually have to consider it as the slightly smaller Temperly-Lieb category. Okay, so the point is we have that this Temperly-Lieb internal Skein algebra, so the Skein category when you basically only have one point, is just this stated Skein algebra with these generators and relations here. And the other thing is this is all kind of topological. the other result is using the relation to some load of other stuff, we can actually work out what a presentation of this thing is. Or in particular, if you consider a Lie group, and then you consider the quantum group associated to this Lie group, and just the standard R matrix of this quantum group, you can define something called the reflection equation algebra. I've given the reference Majid. It's not because he invented them, as far as I know, but because the reference to Majid has a nice account, which is written down in one place. But basically, a reflection equation algebra is something that has a bunch of generators, so n squared generators, and it satisfies something called the reflection equation algebra equation, which is basically, this is controlled by the R matrix you've chosen, and these U1 and U2s are just the correct tensors with the unit the identity matrix. And so what you do is you do this, and to get the reflection equation algebra associated with the Lie group G, you take this thing and you basically quotient it by one, like a breeded version of your relations associated to G. So in our case, for SL2, we just take this algebra for when you take the standard R matrix of quantum, the quantum group of SL2, and you take these 4 generators, and you quotient it by this braided type determinant. And the point is that this has, and this is essentially some generators, and these are a bunch of relations. So they're pretty concrete as you go. And the point is, if you take the internal Skein algebra, you get that it's isomorphic to a load of copies of this reflection equation algebra. So if we take a surface, so this surface here on the left is actually the 3-punctured sphere. So the first puncture is here, the second puncture here, and then you've also got a puncture around the outside. So if you look at this, this is basically a disk with 2 handles attached to it. And so what we do is we have one reflection equation algebra per handle, and you use a tensor product between them. And the tensor product between them, it just depends on the type of handle. So in this case, these handles have nothing to do with each other. They're just one's on the left, one's on the right. So the tensor product we use is the braided tensor product, which is controlled by the R matrix again. And we have this Skein, internal Skein algebra of this 3-punctured sphere is isomorphic just to the braided tensor product of 2 copies of the reflection equation algebra. This example, and this algebra is also called the Alekseev Moduli algebra because he came up with it long before any of the factorization homology stuff turned up. So just before I end, this picture on the right, if you actually think about it carefully, is going to give you a punctured torus. And what you need to do is you think of a torus, you think of the A and B cycles of a torus, and then you basically use the puncture and then you retract to these 2 cycles. So you end up with is, again, just a disk with 2 handles attached. But this time, the handles are no longer have nothing to do with each other, they're actually interacting. And that means that in your Alekseev moduli algebra, they again just have 2 copies of the reflection equation algebra, but this tensor product between the copies is going to be a little bit more complicated. You can still write down formulas for it, but this is what I mean by this tensor product depends on the type of handle, and basically it depends on the topology of your surface. And I think that's basically it now. So I think there's my references. Well, not a particularly complete set of references, but there you are. And any questions?
Yeah. Before questions, let me actually thank you for the very nice talk. And now you're free to ask questions.
Any questions?
Okay, then I will ask a question. Of course, if you have SL2, it's tempting to just study other cases, whatever, SL3, whatever, type B2. Has anything been done in that direction?
I think, okay, so the reflection the result relating it to the Alekseev moduli algebras doesn't depend on it being SL2 at all. You put it a quantum, it just changes what the reflection equation algebra is. But it's still the result holds. So you kind of do still get a general result. The other thing, if you want to get back to the Skein algebra, you take the invariance. So that it does actually relate back to the Skein algebras, which I should have probably said. But I think in terms of, there's kind of two questions. One is if the Skein algebra has been worked out for that.
Right.
So obviously, if you put the Temperly-Lieb, you get the Kaufman. And I think you do get some results. I think for, like you get Kupenberg for SL3, I think. And I feel the Humphreys have some relation to the SLN, but I don't know how much has actually been done relating the Skein algebras to the basically how you precisely link them to the representations of the quantum groups. Though I think most of the Skein algebras are related to representations of quantum groups.
Right, but you're saying nobody has really done it, right?
I think people have done. Okay. I think there is a bunch of work on relating certain Skein algebras to representations of quantum groups. Probably you could use, particularly for SL3. But I haven't personally. I think it exists, but I can't give you a personal direct reference. This is like, you know, Paul Wedrick would probably be better for me than
right now.
And I don't think he's here.
I have asked.
Yeah?
Yeah, go ahead. Go ahead.
I have asked many, so if
go ahead, no one else seems to be asking.
Okay, so in your theorem, you prove that the Skein category satisfies the excision property. And that means if you have two surfaces, you know how they intersect, then you can compute the result from the original result. So how about if we start with the Skein category of a surface? Can we, in general, know what would the Skein category of the puncture of that surface is? So
if you want to add a puncture to the surface.
Yeah, because that's going to make it more complicated.
You would get a, you should be able to just apply the excision. So if you considered like n punctures and you add another one, you basically are just gluing on a handle to the rest of the thing according to a couple of intervals. And so you would get a description of that thing in terms of the original one with a relative tensor product.
Oh, really?
But I mean, it's not topologically that interesting because you know if you have a tangle in the thing, you can cut the tangle. And that's going to get you tangles in each side. So topologically, all you're doing is you're saying if you have a surface, you just cut a tangle. And unlike in the Skein algebra, because Skein algebra don't allow things on the boundaries, in a Skein category, it works. That's a perfectly fine morphism in your Skein category.
But if you have a puncture in the surface, then the morphism space is going to be much more complicated because the set that you quotient is much smaller.
Yes, because you add a function. The point is what you end up with is a load of tangles. You break them down as, so if you have a puncture, the obvious generator of the thing is the loop that goes around it, right? You break that up into the kind of semicircle, the left semicircle and the right semicircle.
I see. Oh.
So you can't do that in a Skein algebra because semicircle isn't a well-defined link.
Huh. That's interesting, yes.
But for the case of Kaufman, this is the stated Skein algebra, so that was the relations. You obviously have the same excision result there, and it has I think that paper has like diagrammatically how you actually just break things up and what the generators would be geometrically. But yeah, they're semicircles.
I see, and for Skein algebras, you basically get McDonald-like algebras from this, or Dahas.
Yeah, I mean, there's certainly, if you get a 4-puncture sphere, you get the spherical Daha CV, C1. And I think the other ones, I don't know if you can link the punctured torus to the spherical Daha of A1.
Right.
It's a bit of a mysterious connection, you know, in general, but there are definitely relations between these two areas.
Right. So maybe my secret question is, for your work on genus 2, what would the result be if you puncture that genus 2 surface? Would that give you a Shakirov Arthamanov genus 2 Daha?
I'm not
Okay.
sure.
Okay. Thank you. Thank you.
Further questions?
On the result,
Okay, so let's thank the speaker. Again, it was a very nice talk. I turn off the recording so we can ask now questions.